Hello, Professor. My name is Leon Spanner. I'm here today with Angela Zhang and Kiran Singh. We're here to discuss predicting cervical cancer through biopsy results. Angela, please take it away.
So a little background, our team chose this data set because cervical cancer has a high survival rate. So when it's caught early, we have important predictors that we can evaluate that are groundbreaking to the medical field. It is by no means a death sentence, so there's definitely room to save lives. HPV is supposed to be one of the most important predictors, but there are definitely many more that can help doctors diagnose and treat accordingly. HPV does not guarantee cervical cancer and vice versa, so looking into other contributing factors can tell a lot about the problem. Lastly, when deciding between different data sets, we also found that this one in particular had less coverage. So we decided that it would be an interesting task to take on. One thing to know is that the female patients came from an institution in Venezuela. This is extremely important because the high death rates for cervical cancer around the world tend to be in third world countries. So we have a lot of room to help improve this. And the explanation for this is just lack of access to testing. So starting off the project, we load the data set in the format of a CSV, and we removed 3 columns off the bat. We lacked domain expertise on the subject, so in order to yield better results, we ended up just removing them completely. Once we did this, we were able to look at the dimensions of the data set, and we were looking with 858 rows and 33 columns. So we start off our pre-processing step by checking for missing values by column and then using imputation by median to handle them. We couldn't use K and N imputation because we would have ended up with negative values and it wouldn't have made sense for certain predictors. So we had to look at the context of the problem to see if negative values would affect it. And an example would be negative number of sexual partners, which didn't really make sense. The next thing that we did to prepare for the modeling is checking for zero variance predictors. These are the predictors that either have unique values or only a handful of unique values. These predictors can cause instability in modeling or even cause the model crash. So it was really important for us to remove them. We then use the near zero function in the caret package to accomplish this, which removes both near zero variance predictors and these zero variance predictors. And these near zero variance predictors have a few unique values and a large ratio of the frequency of the most common value and the second most common value. And after we did this, we ended up with 20 near zero variance columns with the new data set dimensions being 858 by 13. And now for EDA.
Thank you, Angela. And it was important for us to embark on this next step because before diving into any kind of model building, we have to explore our data because it gives us a nice visual representation. We know what we're working with. We already know the dimensions, right? So now it's up to us to look at the distribution of the data. And just looking at these female patients, we can see from this distribution of this histogram plot that from a numerical standpoint, even based on this 5-number summary, the mean is larger than the median, which gives this a positively skewed distribution. So further, we inspect this by age group to determine which age group has the highest amount of data in it. And here we can see that females age 22 to 30, most of the data is attributed to them. So from here, we want to look at that same distribution, this time overlaid with the actual biopsy results themselves. So for this reason, we look at this contingency table up top, and we see that immediately that there's a class imbalance problem with 803 cases being attributed to or classified as healthy, and only 55 of those being classified as cancerous or positive test results. So from that, we see that 20 of those, which is the highest amount of any age group, are attributed to the 22 to 30-year-old category. So in the event that that's rather challenging to see from a visual standpoint alone, such as this overlaid histogram plot, we have created this contingency table to highlight this numerically as well. Moving it a step further, we see that the histogram becomes normalized. Herein, we highlight our class imbalance problem by looking at the distribution in terms of frequency. For example, 51 to 60-year-olds exhibit 50% healthy results, 50% cancerous results, but that doesn't really do any justice for examining the actual distribution in this data set. So moreover, this class imbalance problem is highlighted here in this visual depiction of biopsy results by class, as well as, again, 803 healthy, 55 cancerous. We move further to examine the correlation between predictor relationships, and we see that there are a few highlighted by the dark orange color. Specifically, we remove STDs and STDs pertaining to condylomatosis from this data set because they are the two highly correlated predictors that were identified. We also look to the relationship between the predictors and the target itself, which yields only one the highest correlation being that for STDs. We remove those highly correlated predictors with this function. Moving on to the next step, we examine principal components with PCA by identifying that 19.8% of the variability in the data is explained by this first principal component. We can see that in this discrete plot of the first 10 principal components, as well as the ensuing table, which highlights the same. From here, we finally get to creating a data partition of our data set because it's important for us to see what is done to the unseen data. So we give it an 80-20 train test split, and we assign predictors to their respective columns and the respective train test sets, with assigning a response variable, doing the same with that, and then partitioning it as follows. And from here, we assign unique train control parameters using the let go of one cross-validation method, which is similar to the Monte Carlo simulation. It takes in a two-class summary function, which is what gives us the ROC, or the receiver operating characteristic metric, which will inevitably measure our performance. We want to see class probability, so we say true. We want to save our predictions. And this is where we finally address the class imbalance problem by sampling down. If we don't, and I have to mention this, if we don't address class imbalance, what's going to happen is on the test set, we're going to see 0% specificity, which is our target. From here, I'm going to say this last thing is that in looking at our first introductory model, we look to the generalized linear model, which we can liken to logistic regression, where it takes in a train function. We put in our train set, our train target. GLM is our method. We assign those train control parameters, which I mentioned above. We pre-process it by centering and scaling. And of course, we use that metric of ROC, which we're interested in. And from here, Kiran will explain further. Please take it away.
Yeah, thank you, Leon. As Leon mentioned in GLM model that we are using pre-process, center and scale parameter, which is required to avoid potential bias and to enable each predictor to contribute equally to building the model and to predict new unseen data. Similarly, we performed other 10 models with the same tuning parameters but with different names. However, few of them are using hyperparameters such as support vector machine model is using sigma and cost parameter. I guess Leon has some good thought on it, why we are using sigma and cost.
I do, and first and foremost, I think it's important to mention that we implement support vector machines for their ability to take the data points within a data set and generate a hyperplane that best separates them by two classes. So we use the margin to calculate performance by taking the distance between the classification boundary and the closest training set point. So this maximum margin classifier is what we often refer to as the support vector machines, hence the name. And more importantly, our data is evaluated using the radial basis function, which is why we assign the method to SVM radial as opposed to a different method. And lastly, the reason we tune our cost parameter as such is because we increase the cost sequence so it's commensurate with the model's propensity to correctly classify a larger portion of the training data. That's all I wanted to add on that note.
Now we move on Penalized GLM Net Model, which is using lambda, length, and alpha values, whose value decide this penalized model is either ridge, lasso, or elastic net. Now we are going to table comparison for train and test data set. We are showing comparison all 11 models like generalized linear model, linear discriminant analysis, mixture discriminant analysis, PLSDA, nearest centroid, GLM net, random forest, neural network, K nearest neighbors, and naive support vector machine with respect to ROC, AUC, specificity, and sensitivity on trained data set. Similarly, for other model and table, we are showing the same comparing all 11 models on test data set using accuracy, sensitivity, and specificity. Now we come to ROC curve. Here we are displaying ROC curve. And ROC curve, what is ROC curve? ROC curve is a graph showing the performance of a classification model at all classification thresholds. A ROC curve is constructed by plotting the true positive rate against the false positive rate. Classifiers that gives curves closer to the top left corner indicates a better performance. As per the plotted ROC curve, we see a healthy ROC curve, and in general, high AUC value indicates better test performance. So in this case, random forest with the black line is the better one. Now we are moving on model comparison summary. Since data set is imbalanced, as we have seen the biopsy result by class, which shows cancer class has only 55 values and healthy class has 803 values on the basis of imbalanced data set. This is a true negative problem since health class is considered as dominating class. That's why we are considering high specificity is better to select a better model to predict cervical cancer in among women. Also, type 2 error is also known as a false negative and can also be called as error of omission. Hypothetical example is test for cancer may report a negative result when the patient is in fact infected. This is type 2 error because we accept the conclusion of the test as negative, even though it is incorrect. Therefore, type 2 error should be low as possible, otherwise it could harm cervical cancer prediction project. As shown, table model comparison summary on trained data set, we have compared all 11 models, and what we are showing, random forest has the highest AUC and specificity, and naive has a highest sensitivity on the training data set only. Similarly, on trained dataset model comparison summary test, it clearly shows naive has highest accuracy and sensitivity, while PLSDA has highest specificity. Overall, PLSDA has come out as a better model since it has above average value of sensitivity, specificity, AUC, and accuracy. If we go with other two top models, then we can conclude naive Bayes and random forest is good. But if we consider as a balanced way, so definitely PLSDA is a better model among all 11s.
To that note, rather quickly want to mention that we can look at performance alone, then of course random forest wins, to your point, Kiran, but we're looking at performance and predictive ability. So this is why we take that balanced approach. I'm sorry for interrupting, Angela, please take it away.
Yeah, so I wanted to conclude by just adding some statistics to the impact of what we did in our project. In 2020, an estimated 604,000 women were diagnosed with cervical cancer globally. And cervical cancer actually used to be the leading cause of cancer for women, but both cases and number of deaths are decreasing with the growth of modern medicine due to availability of testing. So it's our job to really interpret these results and optimize on our access to new technologies in order to potentially save lives. About 44% of the people with cervical cancer are diagnosed at an early stage. So our goal ultimately was to decrease this number and ideally avoid the cases in general.
Thank you, Professor, for your time. We greatly appreciate it. This is a very important topic, and we are glad that we were able to share this with you.
Thank you for your time, Professor. I enjoyed working on this project with my group, and I hope you enjoy our presentation.
Thank you, Professor, for giving such precious time to go through all this presentation.